When Python executes a program, different expressions can be evaluated in different environments. So there can actually be multiple environments in the same environment diagram. We're going to look at one of the examples that I showed you last time in detail with diagrams so that we know exactly what's going on. But first, let's review everything that I told you before about user-defined functions, here on one slide in summary form with all the vocabulary that you need. So first, we have a def statement. A def statement is what creates functions. It looks like this. That whole thing is a def statement, which spans multiple lines. It has a name for the function you're defining, a formal parameter, which is the name you give to the argument of the function. There can be more than one formal parameter, in which case they're separated by commas, one for each argument. The body of the def statement is everything indented after the first line. And in this case, it's just a single return statement, though it is possible to have more than one line. This return statement has a return expression, which multiplies x and x together. When a def statement is executed, a new function is created. The name, which we see here as square, is bound to that function in the current frame. Now, when I've defined this function that squares things, I still haven't actually multiplied anything by anything else, because I haven't called that function yet. That happens with a call expression. So later on in my program, I might say square 2 plus 2. That's a call expression. The operator is the name square. Its value is the function that squares, the one that we just defined. Okay, there's an operand in between parentheses. An operand is an expression, in this case 2 plus 2. It evaluates to a value 4, which is the argument of the function. So, when we reach a call expression, we evaluate it by evaluating the operators and operands, and then calling the function on the arguments. Calling or applying a user-defined function is also a process that we need to spell out. So I showed you a diagram that looked like this, which was the function signature inside of a little tube. In comes the argument, out comes the return value. How does this happen? Well, we start by creating a new frame in which the formal parameters of the function we're calling are bound to the arguments we're passing in. In this case, x would be bound to 4. And then the body of the function that we're calling is executed in that new environment. So we would, in this case, compute the multiplication of x and x, where x is bound to 4. 4 times 4 is 16. Okay, so that's the simplest possible example. A slightly more complicated one is when we import mul, we define square just as we did before. But now we're going to square the square of 3. This diagram indicates that we've already executed the def statement, which bound the name square to a newly created square function, and we're about to square the square of 3. How do we square the square of 3? It's a call expression. So we just use our rule for evaluating call expressions, which means the operator is evaluated. It means the function that squares. The operand is also a call expression, so we need to apply that procedure again. Square is the function that squares, 3 is the number 3, and now we can apply our user-defined function square to the number 3. How do we do that? Well, it has 3 steps. First, I create a new frame. Then I bind the formal parameter, x, to the argument value, 3, and there's the binding right there. Finally, I execute the body of the function, which in this case says return mul xx. So I have to multiply x and x together. I get a return value of 9, and that's how I get the value of this call expression. Now that I know what the value of this operand expression is, I can apply this function square to the argument 9 and repeat the process again. Okay, so that means introducing a frame, binding the formal parameter x to the argument value 9, and then executing the body, which multiplies 9 times 9 and gives me 81. So let's look around here for a second. We have one square function. We created two frames from that function by calling the same function twice. Each of those frames is different, which is why we gave it a different frame label, f1 or f2. It's also different because we passed in different arguments, so we got different bindings from the formal parameter to the argument, and that led to different return values. An environment is a sequence of frames. So far, we've had an environment which was just the global frame alone. We had those before we ever even had def statements. But once we started calling user-defined functions, we started getting multi-frame environments, ones that have a local frame and then a global frame. Let's try to find all the different environments in this diagram. There's one, just the global frame alone. There's another, f1 followed by the global frame. And there's a third, the frame f2 followed by the global frame. So there's three different environments here. None of them include all three frames, but there's one environment per frame. If you start with a particular frame, you can always find the whole environment just by following the parents of the frames. So let's say we're interested in the environment that starts with the frame f2. Well, we know the next frame is the parent of this frame, which is the global frame, says right there. Global frames don't have any parents. They're always the last frame in an environment. A very important point is that names have no meaning without these environments. These are the things that endow mul and x and square with some sort of meaning, some value. Every expression is evaluated in the context of an environment, which allows us to figure out what names mean, and a name evaluates to the value bound to that name in the earliest frame of the current environment in which that name is found. In this case, when we evaluate mul xx for the second time, it's in an environment that starts with the frame f2 followed by the global frame, and we have two different names we have to look up, mul and x. So when we look up x, the first thing we do is look in the first frame of the current environment. And we find x there. So this is the earliest frame of the environment in which x is found. So x is 9. When we look up mul, we first look in f2 to see if mul is there. It's not. So then we look in the next frame of the environment, and lo and behold, there is mul, bound to the function that multiplies. So that's another case where we found a name in the earliest frame of the current environment in which that name was found. It just happened to be the global frame. But we did check f2 first. Names can have different meanings in different environments, because each frame can have a different binding for the same name. In particular, a call expression and the body of the function being called are evaluated in different environments. Here's an example where we use the name square for both the name of a function and the name of the formal parameter. Def square square, return mul square square. Now I'm not recommending you do this, but if you square 4 in this case, you really do get 16. Why is that? Well, in the environment diagram for this example, there's a global frame in which square is bound to the squaring function. There's a local frame in which square is bound to 4, because we call the squaring function on 4. So the difference is that when we evaluate square 4's operator, we're evaluating that expression in the global frame. That's the call expression. It's not indented at all, which indicates that it gets evaluated in the global frame. On the other hand, this line is indented. It's part of the body of the square function. And so it's always going to be executed in an environment that starts with a square frame, because we create this frame and then we execute the body. So this square is evaluated in an environment that starts with f1 followed by the global frame. But when we go looking for what square means, we always look in f1 first. There it is, and we found 4. So we never find this binding because we're only interested in the earliest frame of the current environment.